the last talk of the workshop, and pleasure, the privilege goes to Piotr Fryzlewicz. I'm not sure if I butchered the pronunciation of that.
That's good, perfect.
Wow. And he'll be speaking on multiscale methods in recursion and data science. Piotr?
Thank you very much. Thank you, Richard. And this is my first time to be the last speaker at any event. So I'm going to enjoy it, and I'm going to start by thanking the organizers of this workshop and the organizers of this program for putting together clearly another fantastic event at the Isaac Newton Institute. Every time I'm here, I see a lot of the top people in the field, and I have the opportunity to talk to friends. So that's really it's really a fantastic event, and it's a great honor to be here as a speaker as well. So thank you very much, and I'm going to get going. So yes, multiscale methods and recursion in data science. That's obviously a very generic title, and I'll try to make it more specific and focused as I go along. So and I know that some of you have heard bits of at least the introduction, but I promise there'll be some interesting new material later. So I'm going to start by saying that obviously a lot of the stuff that's going in modern statistics these days involves estimators formulated as optimizers of certain criteria, typically, for example, involving a fit to the data plus a penalty. And it's often the case, inevitably perhaps, that as they get more and more complex in nature, we often require more effort to actually compute them, and also to an effort in the sense of computational time, perhaps, but also in the sense of computational expertise. So even things like the lasso, some people will wonder if they can compute the lasso, if they know how to compute the lasso, if they don't know linear programming. Turns out it's possible, but there are all sorts of questions like this, and even today we had a very interesting talk about bounded variation, multiscale image denoising, and then again how to compute this estimator. That's a separate non-trivial question. So what we try to advertise, not only in this talk but maybe even more generally, is estimators which are already formulated as algorithms. So there's no extra optimization bit that's attached to it. I don't write an estimator as a minimum and then I still have to compute it, but I write an estimator and I think of an estimator as already an algorithm. So this helps in this can help with some of the issues I mentioned. For example, if I write an estimator as a minimum and then I still have to compute it, then perhaps I've analyzed the theoretical behavior of the minimum, but I'm missing out on the theoretical understanding of the error involved in the process of computing the estimator. So this I don't control, and that's on Wednesday we had a very interesting talk by Johannes from Leiden University, who talked about the statistical theory for deep learning, and again that theory only worked for the estimator written as the minimum of a certain criterion, but there was not even a mention of the error involved in computing this estimator. But clearly that's almost all that deep learning is about, how to quantify the error coming from the very complex optimization. Whereas if you think of an estimator as an algorithm, then either you know how to control the whole estimation error, or you have no idea about how to do it. But you don't have this problem with the optimization part introducing unknown error. And also sometimes formulating estimators as thinking of estimators as algorithms can also help in the theoretical analysis. So I'll try to say a bit more about this later. Great. So now on to, so if I now okay. So what is a multiscale method or a multiscale algorithm? Well, very roughly, is a method, is a statistical method that performs similar actions on the data at various levels of resolution, and that's typically done with the aim of combining some sort of global and local information from the data. As examples, we can think of, for example, wavelet transformations or wavelet-based algorithms for smoothing and similar tasks, or adaptive wavelet transformations, where I choose the basis from the choose that wavelet basis from the data, or for example things like binary segmentation for change point detection, which is also so it's also a multi-scale method. And I will say a bit more about binary segmentation soon. So I don't want to. Okay, so I'm going to skip this part because a lot of people know about wavelets, and this talk is not about wavelets anyway. So maybe let me skip this part apart from saying that this talk will be a lot about recursion, the use of recursion in multi-scale methods. So multi-scale methods are naturally amenable to being coded up recursively, because I'm performing the same action on the data at different levels of resolution. So that same action can be often captured and coded up recursively. So just to give you an example of what I mean, a simple example involving wavelets. So how to compute, for example, the Haar wavelet transform. I'm sure a lot of you, or if not everyone, knows this. So I take my data x to be the input, and then I compute simple summation and differencing of the neighbors. So firstly, I do it involving data x on input. So I'll be taking summation of, for example, x1, x2, and then x3, x4, etc. And then I'll be doing the same type of summation, but at a different scale, involving the previously computed s's. So there is a recursive thinking in this sort of algorithm, because I'm doing the same operation at various scales. And perhaps it seems obvious to you, but if you think about it from the point of view of even implementation, if you ask ourselves, have we ever seen a recursively, in the sense of computer science, recursively implemented wavelet transform? I haven't, for example, seen this. So people always typically use loops and similar things, whereas recursion, in the algorithmic sense, is not very often seen in this context. Whereas I think it should be, because it's both natural and can often help with many things. So why do I? So in this case, recursion, not in the sense of implementation, but in the sense of writing a wavelet transform in this way, speeds up computation. If we wanted to compute the wavelet transform directly on the data as a linear transformation, then you'll be a lot slower. Yes, and just to advertise recursion a bit more. So let's move on to binary segmentation as an example of a multi-scale algorithm. What does binary segmentation do? It's an algorithm for segmenting data sequences, or finding change points in data sequences, where we first look for one most prominent change point, and then if and once we found that change point, then we split the data accordingly where we think that change point is, and we do the same, perform a similar search to the left and to the right of it. So again, there's a very strong sort of recursive feel to it. We perform the same action on the data at different levels of resolution. Firstly, on the whole data set, we perform change point detection on the whole data set, and then to the left and to the right of that change point, and then we always go left, go right, go left, go right. So this makes the procedure naturally recursive, and this has at least two benefits in this context. It makes it very straightforward to implement. We just need to, so the recursion literally, if you implement it recursively, takes 2 lines of code. This doesn't necessarily apply to some other change point detection methods I've seen recently, which are can be very complex. And interestingly, also for example, the proof of consistency of binary segmentation is also has also a recursive structure. So in some sense, it follows the flow of the method. So in other words, thinking of multiscale methods as recursive programs can have many benefits. For example, this sort of implementation can speed up computation, can make the computation, can make the implementation easier, but also can help us direct our thoughts in a certain direction, certain sort of recursive direction, which makes them easy to analyze theoretically. Yes, so that's exactly what I just said. So this talk will be about yet another possible benefit of this sort of recursive thinking in the context of change point detection. So I'm going to talk about a recursive modification to another change point detection method, which I worked on previously, which has very clear benefits in terms of the accuracy and computation time for this method. So let's make a start by defining the model, and the model will be very simple. Will be a sequence observed with noise, and if we want to detect change points, so this is when I say a sequence, what I really mean is a piecewise constant sequence. So this sequence f of t will have some sort of jumps, and the locations of those jumps and the number of those jumps will be unknown and have to be determined from the data. So our task is precisely that. And what we typically see in the literature is, I think, still two broad classes of solutions. One that is trying to estimate all change points at once by exactly the sort of technique that I mentioned at the beginning. So by writing the likelihood type of fit for the data plus penalty for the number or locations of change points, and that's fine. So that to me, and of course, that there are some fairly successful procedures within this context. But to me, the single biggest problem with this class of methods is that it's often unclear what penalty is best. So I've never seen a penalty that works well for various classes of signals. For example, for signals with frequent change points and for signals with infrequent change points. And yes, so some penalties work very well for one or the other, but not for both at the same time. And then there is a class of methods which estimate change points sort of one by one rather than all at once. And binary segmentation is in this class, of course. Binary segmentation in the sense that I described before, where we first look for one most prominent change point, and then we split the data, and then go left, go right, etc., etc. Some methods, which class they lie in is sort of less clear. Sometimes we can argue that this method is in neither class or is sort of in between the classes. So binary segmentation is of course, as I mentioned, is extremely the recursive character of binary segmentation makes it very simple to code, and also is possible to analyze it theoretically in this way. But it has a lot of problems, and if you heard me talking about change point detection over the past few years, then you have heard this before. So, for example, if you consider binary segmentation for these data in black here, so we don't observe the thick line, we only observe the thin black line noisy data, and we trying to estimate these three change points. So what we do first is what binary segmentation is telling us to do first is to compute a Q-sum statistic involving this entire data set. A Q-sum statistic, again, I'm sure you all know what it is, and if you don't, then think of it as a measure of the least squares fit to the data of the best function containing one change point only. So imagine I'm trying to fit to this data set the best function containing one change point only. And where this blue line is maximized is where I think the change point lies if I use this criterion. And clearly, I'm very far, so the maximum is exactly here, which is very far from any of the change points. And the reason it's far is because this particular data set has three change points in a very sort of awkward configuration. So if I try to fit a model with one change point on the whole data set, then you can see how it will not know where to look. So from the point of view of fitting a function with one change point, it's almost like there are no change points at all in this signal. Okay, so the fit will be very poor. So what we can do instead is we can zoom in on this feature, and we can start our Q-sum statistic not at the beginning of the data set, but more like here. So think of starting at 100 and ending your Q-sum statistic at 200 perhaps. And now this feature in the middle appears to be more prominent from the point of view of this zooming in. And I can indeed, if I do the Q-sum statistic on this shorter interval, then I can locate my change point better. That's the maximum of the red line here, and the location in fact corresponds exactly or almost exactly to this change point in the middle. So zooming in gives me a clear benefit from the point of view of my task here. But of course I don't know where to zoom in. That's the whole point. So what I proposed in my earlier work from 2014 was what I called wild binary segmentation, where I don't maximize the Q-sum over the whole data set, but I draw randomly sub-intervals of the data. For example, use the board. So if this is my data set, I draw randomly some intervals, sub-intervals of the data, perhaps uniformly with uniform start and end points, and then I fit my Q-sums not just on the whole data set, but on each of those sub-intervals separately. So there'll be some Q-sums on each of these intervals. Perhaps like this, and then I choose as my first change point candidate, the Q-sum that maximizes, so the maximum Q-sum over all those intervals. So in this case, you mean maybe this one here, and if this passes a significance test, then I do the same to the left and to the right. I repeat the same procedure to the left and to the right, and I don't need, the nice thing about it, so the only thing I need to do is once I found what I think is a change point, I need to tidy up here a little bit, in the sense that I need to remove from consideration those intervals which straddle that previously detected change point. Because I don't want double detection. I want to remove this interval from consideration, for example. Okay, so then I go to the left and to the right, and the good thing about it is that I can reuse previously drawn intervals. I don't need to draw new intervals to the left and to the right to detect further change points here. So this this was the idea from this earlier work, this procedure by being able to zoom in. So the length of the intervals are random in some sense because I choose the start points and the end points uniformly. So from this point of view, this procedure adapts in some sense to any sort of change point landscape in the data. Whether I have very local features or very global features, I can, if I draw a large enough number of intervals, I can be sure that there'll be an interval which provides a good enough length for me to look at the data to locate the corresponding change point. And another nice thing about this method is that essentially I don't have to redraw intervals each time. So I can reuse intervals. I can reuse previously drawn intervals. There's no point for me to draw new intervals. So this procedure was shown to have a lot better properties than standard binary segmentation from the point of view of both theory and practical performance. When I say theory, then what I really mean is showing that this method makes sense for. Sorry, you have a.
So while doing this, do you make some correction to adjust for the fact that different intervals might have different lengths?
Yes. So the Q sums are always normalized, so that they in some sense have the same variance. They are normalized so that they have the same variance, or in other words, they have roughly the same level regardless of the length of the interval. And this normalization is quite natural because if you think about fitting by least squares, the best functions with one change point to your data, the least squares measure, the residual sum of squares, will be roughly comparable regardless of the length of the interval. Or residual mean of squares rather than sum of squares. So from that point of view, there is normalization to the Q sums. Great. So that was that. Now, so I still think of wide-band segmentation as one of the state-of-the-art methods. Actually, I know I shouldn't be saying this because it's my work, but if you look at what's available on CRAN, for example, then it does pretty well against many competitors. But the problem with it starts when I have many frequent change points, for example. And the reason that this may be a problematic situation for wide-band segmentation is that, of course, if you think about it, I do need to draw. So looking even at this, I'm not sure if I even can read this illustration myself at the moment, but you can imagine that for me to be successful with wide-band segmentation, I need to draw a large enough number of intervals to cover all change points. If I don't cover all change points, then I failed by design in some sense. So you can see what may happen with this signal here. So let me just explain what the signal is. So clearly that there are 1,000 data points, and the signal oscillates between 0 and 1, such that each segment has length, I think, 5. So it's very frequent change points, and of course, what I really observe is a noisy version of it. So I'll be observing something like that. And you can see if I just apply the straight wide-band segmentation with the recommended version of recommended number of recommended number m of intervals, then this is what I get. So I have failed to detect most of the change points, and this is not so much the fault of the method itself as it is a problem with the choice of m, because I haven't clearly chosen m to be large enough. Now, if we look at the paper that described the wide-band segmentation method, then you will see that in the paper m needs to be larger than a certain quantity involving both the sample size and this quantity delta t, where this quantity delta t is the minimum distance between change points in the data. So of course, in some sense, it's impossible for me to choose m on this basis because I don't know what delta t is. Okay, and if I set an arbitrary recommended value, then you can always find a signal which provides a really bad which results in a very bad reconstruction. Yes, so that's what I just said. So the question is whether I can simply increase the number of intervals, and yes, of course I can do that, but this will come at the cost of increased computation time, of course. So if I draw more intervals, then I'll have to pay more computational time for it, and maybe I don't need to do it because perhaps I have one change point in my data. So why should I increase m from something which is already a fairly substantial number to something even higher? So the question is, and that's the question what I'm trying to answer in this talk, whether the procedure can somehow learn from the data, or learn as it proceeds, how many intervals m it needs to draw. Okay. So yes, I have a better reconstruction with a larger m. So here I chose m to be 200,000. But if you think about it, so how many intervals are there for a signal of length 1000? Well, we're getting to this order now. Okay, we're getting to this order. So we're not saving all that much time as compared to considering all intervals there are. You know? So that's should be a source of concern for us, because obviously the whole point with wildband representation is that it's supposed to save you time and be accurate at the same time. So in terms of execution time on a standard Mac, I think, or PC, the reconstruction with 20,000 intervals took half a second, and 10 times more took it took 10 times longer. So that's sort of orders of magnitude that we're talking about here. So great. So the question is, such a large value of m is not needed when we have a limited number of change points, and then the question is whether we can learn somehow how many intervals to draw. And the answer is yes. It's possible we can learn how many m to draw if we think of the wildband segmentation a little bit more recursively. So if we draw, in other words, if we draw intervals recursively as the algorithm proceeds, rather than pre-draw all intervals at the start. So this in this illustration, I meant to also emphasize that in the standard wildband segmentation, we pre-draw all the intervals at the start of the procedure. Okay, and now I'm going to argue that perhaps we don't need to do that. So yes, okay. So that's something I have to clearly explain. So there's a piece of code on the screen. I don't know. Okay. So this, by looking at this code, we can perhaps appreciate the difference between standard wildband segmentation and adaptive wildband segmentation. So what do we have here? Obviously, we have our data x, and if unless x is trivial, we draw our random intervals here in this line. Now, if there is at least one change point, and that's this if here, then we detect all change points we can detect by wildband segmentation with a certain threshold th here, and that's what we do here. So here we detect all change points we know how to detect via standard wildband segmentation. Now, if we now want to do the adaptive version, the version that learns how many intervals to draw and where to draw them, then that's the adapt option. Then what we do is we decrease the threshold slightly. I'm not going to get into details on how to do it because I don't quite know how to do it myself yet. This is just trial and error. We decrease the threshold slightly, and we in each interval. So perhaps I've estimated some change points in my data. So I've drawn a certain number of intervals, and I've estimated some change points. And then what I do is I decrease the threshold slightly, and I run exactly the same procedure in each segment. So I draw m intervals in each of these sections separately. So at the beginning of the procedure, I draw m intervals, and then within each section, I also draw m intervals, unless m is already too many. So I draw either m or as many as there are. Yeah, whichever is smaller. So I do it completely recursively, and intervals get drawn again in each of the segments, estimated segments. So the procedure, in other words, the procedure executes itself, as you can see here. The name is the same, executes itself on each of the segments of constancy with again the same number of intervals m and a slightly lower threshold. Whereas the non-adaptive version, the standard while-variant segmentation, which is this else here, simply returns that estimated signal with these 3 change points, and it stops here. So it doesn't re-execute itself here. So you may ask, so aren't you even slower because you do more here as opposed to less? And the answer is no, because if you opt for the adaptive option here, then you can get away with drawing at the beginning many fewer intervals, because what you want to do what the thinking in this procedure is, at the beginning, in the first pass through the data, you don't necessarily want to detect all the change points. You want to detect at least one change point to keep the procedure going. Okay, because if you don't detect any, then you stop. So your m only needs to be large enough for you to detect at least one change point when there are any. Your task is in the first pass of the data is different compared to standard while-variant segmentation. In standard while-variant segmentation, you want to detect all the change points and go home. Here you want to detect at least one to keep the recursion going, to keep the procedure execute itself on low and lower resolution levels here.
But do you need the consistency for the first step?
Yes, that's a good point. So here the danger is that if you draw too few intervals at the start, then you don't necessarily trust the locations of the estimated change points, and that just comes from the fact that you can imagine why it happens. So the consistency in while-variant segmentation relies largely on this number of intervals m being large enough, whereas here you don't have that. So there are two ways around it. One is to keep ignoring those estimated change points unless you can trust the estimated locations, and that's when m is large enough compared to the length of the intervals you're on. The other solution is to once you've estimated the change point, is to refine the location estimate. Is to refine the location estimator for that change point. So they are both non-trivial from the point of view of what they imply for the consistency proof, etc. But that's also how far I got into in this work. So I can't say anything else because I don't know.
May I ask a further question?
Yeah, of course.
Do you also need to kind of discard a little region around the first detected change point and go further, like what you did? You showed just.
So here, this you don't discard a region around the change point. You discard all intervals that contain that estimated change point.
Yeah.
And that's not the same, because you can these. So if you've estimated your change point here, but perhaps the truth is here.
Right.
So if the truth is here, then even if there's an interval that also contains that truth, then that truth will be too much to the right side of this interval for to be detectable again.
Right. Do you do the same thing?
Yes.
Okay.
That does itself. That does itself in some sense.
Okay. Thanks.
Yeah, because the procedure only executes itself within this interval, which means there are no intervals that contain previously detected change points. Okay, so that's what I get with the adaptive wide variance segmentation. Sorry, you got
I have a follow-up question. So, basically, currently you are doing this recursively. So you are discard all the previous draw intervals.
Yes.
So you are not reusing any.
No. That's a good question. I should actually. You reminded me that I should say something else. You discard those intervals. You don't have to discard them. You can keep the ones that sit within the. But then you have to retest them again with a different threshold, because the same threshold. If you do the same interval with the same threshold, then you're not going to get a new change point, because that test already returned no change point. So if you keep those intervals, then you can do that, but then you need to reduce your threshold. So basically, I'm not a Bayesian statistician, but I think there's a Bayesian thinking here. If you in some sense you're using the same data many times, and you know that you've run some tests on these intervals already, and they've returned no change point. So if you want to hope to find some new change points within these intervals, then at the very least you need to reduce your threshold, or better still, draw some new intervals and reduce your threshold. So by keeping the intervals you can do that, but then the point is, I don't know how much you gain by keeping those intervals, because you've already tested them with a certain threshold. So perhaps there's more sort of diversity to the procedure if you draw new intervals and also reduce your threshold. And reducing the threshold is a slightly Bayesian thing to do, because your prior is that the previous threshold doesn't give you change points there. Yeah, because the previous threshold only gives you these 3 change points, but no change points within any of those 4 intervals. Yeah. So that's what it is. So okay. So as we can see now, so previously we talked about numbers of intervals such as 20,000 and 200,000, but now I only did 1,000 intervals, and I did the adaptive version, and the execution time was 1/5 of a second. So and the reconstruction is pretty good. So the reconstruction is better than before. And the execution time is a lot shorter. So I've gained both on the accuracy count and the and in terms of the execution time. So that's great. And just to reiterate some of the things I said, and this is work in progress. I'm not going to show you any theorems at the moment, and I was actually working on it on the train to Cambridge this morning. But to me, in principle, it's a procedure. So even if I don't yet quite even know what those theorems could be, because in the original wide variance segmentation we had a statement that if M is large enough in terms of it being larger than a certain function of the sample size and the smallest gap between change points, then I have certain accuracy in terms of the locations and the number, but clearly this is a statement almost of theoretical interest only because I still don't know how to choose M, because I don't know this delta t, this the gap between change points. So to me, what this mainly does is it provides a sort of an artificial intelligence way of the procedure choosing its own M. So I don't have to touch that part. Yes, of course, I do have to provide some sort of initial M, but the result wouldn't change much if I suspect if I did maybe 100 or 2,000 or around this in this region. Yeah, so it's a way of saying to the procedure, okay, well you choose your own m in a that's the initial m. That's the m for the first pass through the data. How many intervals get drawn at the end of it? I don't know. I didn't keep count of how many intervals got drawn in total. But also a lot of those intervals that get drawn in further passes through the data will be short. Will be very, very short because they will sit within these sections. So so I won't be unnecessarily drawing many long intervals in some way. Yeah. Okay, so that's about the decreasing of the threshold here, and then with this prior information. Yes, so that's what I was saying before. And right, so what's the role of the recursion here? And to me, the role of recursion here, the benefit of recursion, is to provide better adaptation of the procedure to the data. So I adapt the number and the locations of the interval and the lengths of the interval more to the structure of the data than if I were to pre-draw them at the beginning of the procedure. So clearly, there's a very, very tangible benefit of recursion here. Very tangible benefit of recursion. Okay, so that's we're almost there, and let's just have a look at an example. We have the UK house price index from Land Registry. What is it? It's basically monthly prices. Monthly changes, monthly percentage changes in the prices of sold properties in London. We can see so that's from 1995 to August 2017, so mid last year. That's the data set, and of course, on the whole, you can see how that this is almost always positive, and the mean would be strongly positive as well. That's the financial crisis, of course, and there are some other. Yes, I'm not quite sure what this was. Probably the debt crisis or something like that. But anyway, so that's what we have, and yes, that's the adaptive wide variance segmentation estimator, and we can see that from the point of view of where we are, at least with the current observations, there's no Brexit effect observed in the data. Mm-hmm.
Maybe I missed something. Can there be a linear trend or something like that?
So that's the monthly percentage changes. So this is not the this is percentage changes. Sorry, yes, this is not the if I gave you the raw data, they would look pretty much like this. There'll be a strong trend. Then there'll be this is the financial crisis, and then there'll be you would see something like that. Yeah, thank you. That's a good question. So
there's no time. You don't have a time series component in
no. I pretend that the noise is IID Gaussian, and in fact I'll show you the residuals in a second. So you pretend that this is piecewise constant signal plus noise model. Of course, you can come to it as a time series analyst, and you can say, well, I'm going to model it as a time series with a constant mean and simply a time series structure on top of it. And that, there's nothing wrong with doing that. It's just a question of.
When I look at that like a time series, I'm not looking at the number of changes that you have.
You're not going to. No. You're not. You're going to get far fewer changes than that. Yeah, of course. So that's this is a modeling choice we made. We chose to model it as a piecewise constant signal with noise. And now the question is, if I now look at the residuals from this fit, what do I see? And let's actually do that. So okay, so let's first talk about this. So that if I do that, if I fit my estimated and the most recent change, where the current point is August 17, is August 14. So this is August 14 here. And therefore, if you look at for example, the EU referendum in the UK, there was the change doesn't get detected here. So okay, so no Brexit effect, perhaps not yet. Okay, and actually let's look at the residuals. So these are the residuals, and if you think the residuals display some structure, then you're probably right. But in terms of the linear structure, then the only thing that's very obvious is the yearly dependence, 12-monthly cycle. There's nothing in the procedure that would have enabled us to remove this 12-monthly dependence. So we're not surprised it's still there. But in terms of other time series structure, at least at the serial dependence level, there's not much there, you would argue. So back to Richard's question, if I now said, okay, I'm going to use the model which is, say, the piecewise constant mean, I'm going to revisit my data, I'm going to use piecewise constant mean plus a process which only has dependence at lag 12, then it wouldn't be at least a ridiculous choice. We wouldn't reject this model right away. Of course, with his expertise, Richard might come to it as a time series analyst and say, okay, I'm going to use a constant mean plus a more complex time series noise, and that might be a good choice as well. So, as I always tell my students, and they're always very surprised to hear it, there are often 2 or more good models for the same data set. Yes, so let's start. And what about the sales volume? Well, here clearly there's no use pretending that we have IID Gaussian noise, so we need to do something about this. So that's this is the sales volume over the same period in London. Firstly, there's this spike here. I don't know. It doesn't look to me to be very genuine, and I think as far as I remember, it's something like it's 17,000, where the neighbors are more like 7,000. So perhaps it should be 7,000, and I don't know. I don't know what that is. So I removed it, and yes. So instead of doing trying to find all the change points, clearly the procedure would have adapted unnecessarily to those tiny movements. I just found the 8 most prominent change points. So the procedure, this gives us a whole solution path, fairly straightforwardly, and then you can have, if you after a particular number of change points, then that's easy to obtain. And here I chose 8, and again, looking at the Brexit effect, to this change here, I think there's some sort of color coding on all this, but I can't remember what it is. But I remember that. Oh no, there isn't. It's just it's essentially the most recent change is January 16. So the question is, what about say June 16 or July 16 or August 16? That is not very apparent from this yet. But of course, buying a house or selling a house takes time. So maybe we shouldn't be surprised that this is not in the data yet. It would be good actually to revisit this data set in a year or 2 and see what happens. Okay, so I think I'm pretty much done. The main reference doesn't exist yet, so this is not a paper yet. But I've been brave and I've already implemented it in an R package that's on the web that does it. So all the examples, for example, in the talk come from this R package here. And okay, so thank you very much.
Any questions for Piotr?
I think I'm still interested in how you decrease the threshold. Like, what's your?
Yeah. Well, that's a good question. For now, I only have a very heuristic way of doing it. So you can't essentially. You obviously have shorter samples, but you can't fully take into account. So you can't pretend. So if your original threshold is let's say of the order of square root log t, and then you go down to your gap between change points is delta t. So potentially you can go down to a sample size of the order of delta t, say. And then you may be tempted to use a threshold of the order of log delta t, but that's too low. You're not going to, by doing this, you're not going to get out of the multiple comparison issue. So you need to somehow, you need to go down, but you need to perhaps keep the same order. You need to keep the same order so that overall you're in a global region of global consistency. But how to do it exactly, and what the constants are that you allowed to operate between, I have no idea. I just did some very rough manual, trial and error type of stuff. From the sort of consistency point of view, it's not a problem because there's a range of constants that give you consistency. So I'm not worried about that, but I'm more worried about fine-tuning practical performance.
Piotr, I think this is related to what I just asked just now. If I understand correctly, there are a few tuning parameters you need to choose for wide binary segmentation. And in that case, is it possible, say, for the first step, instead of using wide binary WBS in the first step, we use a moving window, and computationally it's cheaper, and it will at least guarantee that you go through the whole time course.
That's true, but the moving window, that needs a window parameter from you.
You need 3 parameters for WBS, right? You need the upper, lower bound for the random intervals. You also need to kind of discard a little bit.
Upper, lower bound for the?
Randomly choose a range of intervals.
So you only need to, you only specify M and then press the button and that's it. So the lengths get chosen randomly. You don't choose the main, to me the main advantage of wide binary segmentation is that it chooses, it chooses a random range of lengths for the intervals. So in the thing is with the moving window, I love the moving window approach, but it has some intrinsic problems to me. For example, if you have one change point, then the optimal way to look at this one change point is to look at the whole data set.
Right.
But if you have a structure like this, then the optimal way to look at the structure and to detect the middle change point is to look at this data set. So, for example, if you approach this data set with if you use the moving window approach, and then this is not, then what you do is not optimal because your window is too short. and here, to catch this one and that one, your window will have to be even shorter. So it will be suboptimal for at least for this case. Now, wide binary segmentation avoids this because it will give you an interval which is approximately that long, and it will give you an interval which is approximately that short. So it really it's an adaptive way from the point of view of looking at the data at the right resolution level. And I agree that there are parameters to be chosen, and one of the parameters is the M parameter, and that's what the whole talk is about. So the whole talk is about avoiding having to choose this parameter, which is crucial, and I agree. The threshold parameter is less crucial in the sense that it more is known about what is a good threshold and what is a bad threshold, and that's sort of more universal across many signals and many and values of M, etc. So that's an orthogonal parameter in some sense, and it's a parameter which is better understood. There's less of an issue. To me, the biggest issue would be, if I were to replace it with a moving window approach, would be choosing the window size.
I may have used your WBS wrongly, but let's talk about it later.
Okay. Okay.
So this might be a silly question, but a bit of a follow-up on what E asked. What's the advantage of choosing random intervals to choosing random moving window sizes? So you could randomly choose a bunch of moving window sizes to go through the whole thing, and I guess going all the way through is linear in the number of things. And if when you're randomly selecting the lengths of the intervals in the wild binary segmentation as uniform at random, then that's still going to be of the order of the number of the computation time will still be of the order of the length of the series. So would you not get for free, essentially, rather than computing it on this interval, you do the whole moving window thing and you get sort of the optimal interval of that size rather than the randomly chosen one of that size?
Isn't it? It may be of the same order, but it'll be just algebraically more expensive because you'll be doing more things. No, I mean it's
There's sort of a factor of 2 or something, isn't it?
Right. Also, another question is what you do. Yeah, you could be right. Another question is what you do on each window. Do you go through the whole QSUM, or do you do that just the middle point? Middle point. Yeah, you could. I think this you could do. Yeah. You can randomly draw window sizes, and you can do exactly what you described. Yeah. In fact, partly in response to this, I also noticed that if you do too many intervals, that's also not good, and that's a paradox which I find very interesting. So, for example, if you do all intervals, you don't care about computation, then this really pushes up the threshold in the null hypothesis case. For you to have no detection for the constant case, you need to push up the threshold sometimes quite unreasonably, especially for short intervals. And that's fine to do as long as you have no change points, but then this high threshold starts to hurt you if you have change points. So this we can experiment with what you suggested. It's perhaps a separate matter to say that having too many intervals is also not good. And I was surprised to discover it.
So there's some sort of regularization happening, I guess.
Yes, perhaps. So it's good to have. Maybe it's good to have some diversity in these intervals, which I don't claim to have known this before I designed the procedure, but it's working pretty good from this point of view. Yeah.
In breakfast, is it just do meaning changes or?
For now, yes, but it's a good question. So I'm trying to develop this package, and I have a postdoc working on something similar for trying to find changes, any distributional changes. So you still have an independent sequence, but you don't know anything about the nature of the change. It could be in any aspect of the distribution. And he's working on that. The mechanics of the procedure will be the same, but we will be looking at distributional changes, and that will be part of this package, right? Yeah, thank you.
Any more questions? If not, let's thank Piotr for a really enjoyable talk.
Thank you very much.